Let's now take a look at ShellSort. ShellSort is considered an efficient sorting algorithm. It is its big O is less than n squared. As such, it's efficient. But a lot of researchers don't agree exactly on the order of this particular algorithm. N to the 7/4 is a common number that is often put forth. That's approximately n to the 1.4 or so. This approach is called also the diminishing increment sort, and it was developed or invented by Donald Shell back in 1959. This is an in-place sorting algorithm, so it sorts the data in place, and it generalizes exchanging data items by using insertion sort or bubble sort, something along those lines. We'll look at that in more detail. So we begin by starting the comparison of elements that are very far apart, and we eventually get down to where we're doing that with elements that are adjacent to one another. And making those far apart moves gets us closer, and that's where the efficiency is gained. So while there's no specific algorithm given for the actual the sorting of the subarrays, insertion sort, a modified version of the insertion sort, is normally what's used. And as we've pointed out, for insertion sort, it can tend to go all the way down to order n if the data is already sorted. So in this case, the data is largely sorted after we make some of these far apart moves and bring it in. And so insertion sort is a good algorithm to use because it actually benefits from a list that is more closely sorted, or a sequence that's already more closely sorted. So we will illustrate how to conduct ShellSort on the next slide. So the example that we will show does what's called a 5 sort. That's a gap of 5 elements, and then continues on to a 3 sort. That's sorting items that are 3 elements apart, and then finally finishes with a 1 sort. In each case, it's important to understand that the subarray that we're taking a look at is a logical subarray. So this is an in-place sorting algorithm, so we're not maintaining a separate array. We're just choosing to not consider some of the data items. And hopefully the example will make that more clear. So here is a sequence. You see the data before the 5 sort. So this is our starting data set, and the idea is we want to sort this particular array of numbers, and we begin with a 5 sort. Now what we do to pick a 5 sort is we will end up with 5 sublists, and the elements that we will consider are 5 units apart. So if I consider the 10 at index 0, then I go index 1, 2, 3, 4, 5. I add 5 to index 0, and I consider the value at index 5, and then I add 5 more, and I consider the value at index 10. Let's add the indices up here just to make that more clear. So that's a 3. It's supposed to be a 3. It's a 4 and a 5, a 6, 7, 8, 8 and 9 and a 10. Okay. And let me see if I can make my 3 a little bit more like a 3. Okay, so again, we're going to consider elements that are 5 units apart, and we're just going to sort those elements. So in this case, I'll sort the values at 0, 5, and 10, index 0, 5, and 10. And in this particular case, I'll only sort the values at 1 and 6 because adding 5 more to this would take me beyond the array bounds. In this case, I'll sort elements at 2 and 7, then 3 and 8, and then 4 and 9, and finally, and at that point we're done because we've sort of wrapped around again to the first one. So sorting then the elements that are 5 units apart, 5 elements apart, I have a 10, a 3, and a 16. If I sort that, I end up with the 3 here, the 10 here, and the 16 here. So all I did was I considered only those values that were 5 units apart, and I shuffled them only between those positions. So I physically moved the 3, which was previously at index 5, I moved it to index 0. And the 10 was previously at index 0, and it got moved to index 5, and then finally the 16 remained in index 10 because it's the greater of these 3 numbers. Okay, so looking at the 8 and the 22, that's already sorted, and so this is what I end up with. They stay in place. Looking at the 6 and the 1 needs to move here and the 6 needs to move here, and that's what happens. Here's the 1 and then there's a 6. Looking at the 20 and the 0, 0 is less than 20, so it should go to the left. So here's the 0, here's the 20. And finally, looking at the 4 and the 15, that's already sorted, so that remains in place. And now if I take a look at my array, it looks like this. All right, so I've completed my 5 sort, and my array now looks like this. So you notice that we have gotten some items closer to where they belong. We have some low items in this half of the array. We have some higher valued items in this half of the array. And we're now going to do a 3 sort on this particular array. We don't return to the original array. We're going to do a 3 sort, which means we're going to sort the elements that are every 3rd index. Okay, so 0, 3, okay, 6, and 9. We'll sort those, and then we'll sort the values at 1, 4, 7, and 10. Then we'll sort the values at 2, 5, and 8. And since those are our 3 lists, because we're doing a 3 sort, we end up with 3 lists. That's it. Okay, so let's look at these top 4 numbers. The 0, the 3, the 0, the 22, and the 15. If we were to sort that, we would get the 0, the 3, the 15, and the 22, and that's what we bring down here. Okay, so you see that I've taken the 3, 0, 22, and 15, and I've made it 0, 3, 15, and 22 because that's the ascending sort. Let's look at our second sublist. It's made up of the 8, the 4, the 6, and the 16. If I order those in increasing order, it's the 4, the 6, then the 8, and then the 16, and that's what I have here. Here's the 4, the 6, the 8, and the 16. I do not move those numbers anywhere other than the numbers that I'm comparing them to. Okay, so finally, I have the 1, the 10, and the 20. That list is already sorted. And here's the 1, the 10, and the 20. And if I bring everything down, I've moved the 0 now, so it's here. The last thing I saw was a 4. Here's a 1. Here's the 3. Here's the 6. Here's the 10. Here's the 15, the 8, the 20, the 22, and the 16. And at this point, after the sort, and my data looks like this. Okay, so after the 3 sort, my data looks like this, and I now call just regular insertion sort on this data and on this particular list. Okay, I call insertion sort on this particular list, and it sorts it in ascending order for a final sort. So again, the benefit here is that we begin the process by moving items that are pretty far apart. We're going to move those to sort of the correct end. It's not total. As you notice, after the 3 sort, there's still some things that are in error here. But a lot of the elements are already in their correct place. And the reason why we use insertion sort is that insertion sort is sensitive to the order in which the data finds itself initially, and can benefit us if that data is nearly sorted. So as we make these wide gap sorts and we narrow down that gap, our data is becoming increasingly more sorted, and we're able to gain the value from this particular approach. So that's ShellSort in a nutshell. The math for proving the order of this algorithm is fairly complicated, as I mentioned previously, a lot of researchers don't even agree on a single proof for this. But you can think about it as being roughly around its order n to the 1.5, roughly. Okay, here is a ShellSort implementation from another textbook, and you notice that it has the modified insertion sort, which it calls insort 2. And the only difference between this and the insertion sort that we've previously looked at is that this element called this parameter called an increment is what's used to bump up the array count. So instead of bumping up this array count by 1, we actually bump it up by increment, and that allows us to skip the things that we're not interested in and to only focus on the elements that are increment apart. And you notice that at some point we will continue to decrement increment all the way up until we're down at increment 1, and then it's a complete sort. So the actual ShellSort algorithm is fairly compact. As you see there, it's about 4 lines, and again, it relies on the modified insertion sort routine that you see above, which is 5 or 6 lines.